Here's a circuit. We've got an EMF and 3 resistors and 2 switches. So the question is simply, what switch configuration draws the most current from the battery? So switch configuration just means, they're labeled S1 and S2, open, 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 close, close, open, close, close. That's the question. How would we arrange these switches to get the most current out of the battery? All right, so in any case like this, you can always start all the way at the battery and say, I know that the EMF coming out of the battery, the battery has an EMF, E. It's always going to be a total current times some equivalent resistance, in the case that it's just it's an all-resistive circuit. So really, the name of the game here is to figure out what configuration gives you the lowest equivalent resistance. So you kind of have to look at it and figure out, is it parallel or series, or what kind of a resistor combination is this? So we can start by saying, let's just close the switches and just figure out what kind of a combination do we have here. So I know people struggle with that a lot. Are these in series or parallel? And probably the best way to think of it, if you need a procedure, is just to follow the current. And if you can go through everything without ever splitting the current, if the wires never split, then it's all in series. For example, if none of this were here, and I just went through this one resistor, that resistor would be in series with itself, of course. Say there were another one here, though. So if I just went around, I could go all the way, 2 resistors, they would be in series. But of course, that's not what really happens. In this circuit, here the wire splits, which requires parallel. Every split puts 2 things in parallel, essentially. Right? Now, do they stay in parallel? Yes, because then they split when they come back. So that's why these 2 are in parallel. So you might look at this and say, now, is this one in parallel with this one or this one? And it's in parallel with both. This is 3 resistors in parallel when the circuits are shut. And the one way you might say, but it seems like, isn't this one in parallel with this one and then this one with this one? Is that always the same? And there are other examples where they're not. Like if you had 2 resistors here and this one came in between them, then it would be more like R3 in parallel with this and then that whole thing in parallel with this. But the reason these 3 are simply in parallel with each other is that the top sides are all at the same potential, 1 wire, is all assuming the switches are closed for now. And the bottom sides are all at the same potential. So because of that, it's R1, R2, R3 in parallel with each other, not as part of separate branches. So we could look at this and say, well then, let's see, if switch 1 is closed and switch 2 is closed, then our equivalent would be 1 over R1 plus 1 over R2 plus 1 over R3 added as, inverses. So 1 over, the sum of those inverted. So that would be the equivalent. And we could sit here and figure out an expression for each one, but what you really need, and you could put 1 ohm in and do that, but what you really need now is to have sort of the conceptual understanding that anytime you have a resistor and you put another resistor in series, the resistance goes up, right? Because series is R, equivalent is R1 plus R2 plus R3, etc. So one resistor has a value, add another one in series, and it has to go up. Parallel is the opposite. If you have one resistor, and if you add another one in parallel, no matter what it is, the resistance is going to go down. If the resistance goes down, the current goes up. So in this problem, it's not really a numerical problem. What you want is as many resistors in parallel as you can get, because the more resistors in parallel, the lower REQ, the higher the current, because there's a constant EMF. So that's why the answer actually is both of them closed, because that puts 3 resistors in parallel. Let's look at the other cases. Let's see, this one closed, but this one open. In that case, you do have a parallel branch between R1 and R2, but R3 isn't hooked up to anything, right? So that would be 2 in parallel, but not as low of a resistance as having all 3 in parallel. Let's see, this switch closed and this switch open. Well, then you have these completely disconnected, right? Because they have to come up to this wire and, it's not hooked up to anything. So if this one's open, you only have R1. If this one's open and this one's closed, we just did that. What if they're both open? Irrelevant. As long as this one is open, this branch is doing absolutely nothing, and you just have R1. Okay? So that's how you answer this one. Completely conceptual. Could I make it numeric? Yes, I could. I could pull that off. I could do that. So that's the end of the answer. But if you want extra, here you go. Here's the extra. If you insisted on making this a more numerical computational question, you could say that S1 R equals 0 when it's closed, and R equals infinity when it's open. And S2, R equals 0 when it's closed, R equals infinity when it's open. And then you would need to put those into the equations and just see what happens. When you put zeros, you get 1 over 0, you get infinities. Put infinities, 1 over infinity is 0. It's not usually a good idea to play with zeros and infinities, but you'll get away with it this time, and it'd work out. So you could do that. Now your network's going to get a lot more complicated because now we have things in series and things in parallel, etc. So I'm not going to sit here and do it because I want you to just think of it the first way we did it. But you can, if you're in a little bit of a bind, think about putting in zeros and infinities. So let me give you a small example. So say we were going to have this switch opened or closed. If we have this switch opened, then basically we have R2, let's just do a sort of a fraction of it, switch R3. Now don't worry about R1 for now. We have these two things in parallel. 1 over R2 plus 1 over R3 equals 1 over R EQ, say. Well, what if we have the switch open and call it infinity? What are these two? These two are in series. So you would add them. It would be 1 over R2 plus 1 over R3 plus infinity equals 1 over R equivalent. What is R3 plus infinity? Infinity. Infinity plus any number is infinity, except negative infinity. What is 1 over infinity? 0. So then, in that case, that switch is open. It's really just acting like R2. Right? What if that switch is closed? Go through all this stuff. 1 over R3, 1 over R3 plus 0. Okay, then it's just acting like the two switches in parallel. So you could go through and actually do it this way, if you want to.